So today we will be talking about short-time Fourier transform, its definition, properties, and we will present some examples. Discrete version of STFT is called Gabor expansion. So our first question is, what's wrong with Fourier transform? The answer is, of course, it is nothing wrong with Fourier analysis, but what happens? Actually, after integrating of our signal over t and actually our comparison function, time axis disappears from the result, and we have only omega, we have only frequency content. Of course, time relations are not lost. We know that there is an equation for inverse Fourier transform. We can come back from x of omega to x of t, but definitely it is not, the result has no explicit time dimension. So from time to time, we really need it. This is one possible example. In our example, we have a signal which consists of two signs. One sign, the first one is of 1 Hertz, and the second one is of 4 Hertz frequency. If we look at the time domain, we can see when some sinusoids start and when they end up. But on the right-hand side, you see the modulus of its Fourier spectrum. We can see two hills. The tops of the hills corresponds to the frequencies, so we can easily see that there is something of 1 Hertz and there is something of 4 Hertz inside, but we cannot see when it started and when it ended up. And from time to time, we need something different. Last time I just mentioned music. Music is a sequence of frequencies, sequence of sounds over time, and we need both. So we would like to have some kind of transform that provides both viewpoints from time axis and as well as from the frequency axis. So what to do? Let's go back to the Fourier transform. We can say that the problem is that actually we compare the input signal with something that is cosine and sine. Second term is actually cosine and sine. And cosine and sine are not, they last forever. First, it is very difficult to calculate where is it center, so where they are everywhere, or one can say nowhere. So we must introduce some third term, something that will provide for localization in time and probably in frequency domain. So instead of having pure cosine and sine functions, we are introducing G, which is some kind of local window with desired properties in both domains. And once we have such a window, we are going to shift it to the left or to the right over the time axis to achieve some kind of resolution in time. Maybe I can just give you a couple of examples. How can it look like? So it can look like, so we can imagine that our function G looks like this. This is a possible example of such a function. Definitely it has localization properties because it exists only in a limited amount of time from some, I don't know, we can say a minus a. So it is a rectangular window, or we can choose some other function like Gaussian. Of course, Gaussian lives everywhere, but also we can calculate its effective width. Maybe a derivative of the Gaussian, it is also nice. Second derivative of the Gaussian looks like Mexican hat. Is a very nice also localization window. Or it can be something completely different, like this. Whatever has can have time localization properties. Not only time localization properties, but also some good properties in the frequency domain. So let's go back and see how it looks like. So there are many candidates for good G functions for local windows that we are going to slide to the left or to the right to achieve both insights. The result is called short-time Fourier transform. Our analysis function now consists of two terms, not only this exponential guy, but the product of the two. The result definitely will have one dimension more than the signal, because once you solve that integral, the time axis disappears, but tau remains, as well as omega, both remains in the result. So we will have two-dimensional result. The result will definitely depend on the chosen window. It would not be the same if I have chosen a rectangular window, or it will be completely different for Gaussian window or some other. So now we can ask where that function that consists of two parts, so now it's the product of the two terms, where it is, what is its effective width in time domain as well as in the frequency domain. So let's start with the first question, where it is in the time domain. So this is the equation we have to evaluate. Notice that exponential part, the modulus of such an exponential part is 1. So it does not contribute to the either to denominator or numerator. It just disappears, and the only thing that matters is actually our function g. Probably it's not a miracle, because our function was, what is e to the j power omega t? It is actually cosine plus j sine, and it looks like this. Cosine part would have looked like this, and sine part something like this. And its spectrum looks like this. 2 Diracs. So one can say that our signal in the time domain was completely, it was everywhere. So we cannot find out where is its center, and the width is definitely infinite. On contrary, in the frequency domain, it is pretty much localized. It exists only in 2 points. It is pretty big, but the width is actually 0. So such a weird signal is not a good one to make a proper localization. Okay, let's go back. That camera does not work anymore. Okay, I will just switch it on. Oh, it's better now. Yeah, now you can see the spectrum. I don't know why it stopped working. So the spectrum is two Diracs on two frequencies, actually in 2 points, and the signal was everywhere. Signal was everywhere, and the spectrum was concentrated actually in 2 points. Altogether, such a signal is not, such a template is good for some applications, but not good for localization in both domains. Okay. So we can see that the center in time domain for short time Fourier transform depends exclusively on function g, exclusively on our sliding window function, not on cosine and sine. It disappears from the calculation. And where it is, if you choose symmetric functions, then the center will be 0. But if it's not symmetric, like here, the center will be somewhere, for example, here, and that will not be 0. What happens when you move it to the left and to the right, because we have that shift tau in our calculation, so it moves to the left or moves to the right, depending on the value of tau. We can say that the position of such a local window is directly proportional, linearly related to variable tau, to the shift tau. If we repeat the same calculation in the frequency domain, it looks like this. So we have a product of the two terms. Due to the shift in time domain, we have exponential part in the frequency domain. Due to the exponential part in the time domain, we have a shift in the frequency domain, but the result is pretty much similar. So in time and frequency domain, we have something that looks alike. Of course, this is the time function and this is its spectrum. So the calculation of the center is pretty much the same, and we have the same conclusion. We use the different letter. Notice that we use W just for the frequency here, not to be mixed with omega from our analysis function. So the result is that the center is also can be at 0 if we have a low pass spectrum which is symmetric around 0. But if not, then you have some number right here, and still you have a linear relation between omega in time domain and the center of the frequency in the frequency domain. So both relations are pretty much similar, and we can collect them together and say that we have our energy concentration centers are linearly dependent either on shift or on frequency in both domains. Okay, how about the widths? Once you have the centers, you can calculate the widths. Effective width also depends only on local window g, because e to the power of j omega t, its modulus is still 1. It disappears from calculation. It only depends on the property of our windows in time or frequency domain. And after some calculation, you got some numbers. I can just try to sketch it on our, for example, here you would get some delta in time domain, delta t in time domain, and something, of course, you'll something similar you're going to get in the frequency domain. Of course, you have to calculate the Fourier transform. If it's Gaussian, it will be Gaussian as well. And then you have to calculate the width in the frequency domain. Notice that what is important, that it depends only on the property of our local window. It doesn't depend on cosine and sine part of our analysis function. So altogether, we can say that effective widths are two numbers. Once you choose your local window, localization window, it actually determines what you're gonna get, and they are constant all over the plane for each and every frequency, for each and every time shift. So you're gonna get the same number. The relation between the two widths is given by the Heisenberg uncertainty principle, which means that if you, for example, here you can see two examples. If you choose a rectangular window in the time domain, this guy, in that case, you have sinc function in the frequency domain and vice versa. Of course, if you have chosen the Gaussian, in that case, you have Gaussian in the spectral domain as well. But what happens if you squeeze the left-hand one? Okay, the right-hand one will be wider. So shorter window in time domain or better resolution in time domain corresponds to worse resolution, to worsening of the resolution in the frequency domain. If we just want somehow to present that resolution in this picture, their resolution is represented by circles, its dimensions. So we can see time axis, which is tau, and we can see frequency axis, which is omega. For a given, for some given localization window, we can see some ratio, and let's say the centers of these circles corresponds to the centers of our analysis function. We can put them everywhere on the omega tau plane by changing, of course, omega, and by changing the time shift tau. But everywhere the ratio between the two widths remains the same. If we need better resolution in the frequency domain, in that case, it's gonna the consequence will be worse resolution in the time domain, and vice versa. If we need better resolution in the time domain, things will get worse in the frequency domain. It's given by the Heisenberg principle of uncertainty, and that is a fact of life for the short time Fourier transform. How it looks like? Let's make our first example. Let's apply short time Fourier transform to our two sides. If we apply the short time Fourier transform, for example, at first we have to choose the time window. In this case, it was Gaussian of some size, of some width. When we apply it, what we get a two-dimensional result. Here it is the modulus of our two-dimensional results. We can see two mountains, two hills, that corresponds to two sines. Actually, we can see that these mountains are situated on, they are sitting on different frequencies. This axis is actually the frequency axis. We can read that the top of the mountain is about 1 hertz for the first mountain, and about 4 hertz for the other mountain. Also, we can see that it starts approximately at 0 seconds and end up at approximately 2 seconds. as well as the second mounting starts at 2 seconds approximately and up at the 4th second. Okay, so we have no ideal resolution. So our resolution is defined by the width of these mountains. It corresponds to that uncertainty. On the left-hand side, you can see three-dimensional presentation of our result. On the right-hand side, you can see something that looks like a geographic map as well. So we can do contour plot instead of 3D plot. And the contours are isohypses, so the lines that connects the points of the same height. One can say that probably we should have some idealistic time frequency analysis. I don't know if it exists only in our brain, but one can say that I mean, if you would like to describe to your friend what is really there on how what is really our signal about, so maybe it would look like this. If this is frequency axis, if this is a time axis, maybe you could say that this is 1, 2, 3, 4 hertz. Some idealistic view would look like this. Would be a line. So the first sign had a frequency of 1 hertz. It started at 0. Nothing existed before. It ended up at the second at the 2 seconds, and then in the same time the other guy started and lasted for 2 seconds as well. So this is a kind of idealistic time frequency representation of the phenomenon we're looking at. In practice, instead of that, we got some hills. So we have some kind of uncertainty of even in time or frequency domain. And uncertainties are a kind of a compromise. If you choose different width of your Gaussian function, you can get, this is only an alternative view to the same thing. And if you need a better resolution in frequency, you lose the resolution in time. You are more and more uncertain in time, and vice versa. Seems that Heisenberg was right, and we cannot have both in the same time. So if I just multiply the two widths, if I just multiply the modulus of G in time domain and modulus of capital G in the frequency domain, we can see our analysis space represented by that product. And yeah, if you squeeze one axis, the other one will be widened. So you cannot have them both. Good, but still it is a very nice tool, and when you see something like this, it tells you a lot about the observed phenomenon. There are many technical applications of the short time Fourier transform. Either you can apply it either directly for analysis of something, I don't know, in analysis of speech, it is very, very often used. It can be some kind of predecessor step, something that you do before applying some machine learning system, because if you somehow split the observed phenomenon is some kind of Lego bricks, some kind of something that describes its components, it's going to be much easier to for a machine to learn what is it all about. If you look at the image on the right-hand side, you can see also some effects in between the two hills. Maybe in 3D, this is also visible. So we do not have only the hills, but we have some kind of intermediate values that definitely do not exist in our idealistic view of what we are looking at. Okay, the next question is all information preserved? Okay, our result has one dimension more than the original one, and it would be funny that all the information is not preserved, that we cannot go back from these two dimensions to our original signal. But of course, it depends on our localization window G. So are there any admissibility conditions? Are all G's admissible, okay to do the short time Fourier transform? Can you just put it whatever you can think of, or there are some limitations? The truth is that you have a pretty good freedom of choosing G, and actually the only real limitation is that G must be of finite energy. Let's see why. So how to answer the question, is the information preserved? The best answer is there an inverse equation? So inverse equation really exists. I will not derive that equation. I'm just writing it down. We are going to use some kind of similarity with the Fourier transform. Okay, I will just jump to the beginning. So this is our Fourier transform. Sorry. This is our Fourier transform, and the inverse equation is actually we have to change this sign. So you put the spectrum in. You have to integrate over omegas, of course, not over t. You change the sign right here, and you have to divide it by some constant, and this constant actually depends on it is a kind of a normalization constant, and it depends on the energy of our analysis functions. So let's go to the slide 21. We ended up. Okay, so here we have a result that is actually in the plane. It has two dimensions, time shift tau and frequency omega. So in our result, we don't want to have them both. So we have to integrate not over omega only, but also over tau to get them out. Instead of minus, we have plus. And yeah, it could be a good candidate for the inverse short time Fourier transform. And the result have to be divided by 2 pi. Yeah, it was exactly the case with the inverse Fourier transform, but also with the norm, with actually the energy, the square of the energy of our time window. Now we can see that we need that finite energy, because if the energy was infinite, then denominator would be infinite and the result would be zero, so it's definitely wrong. So any G with finite energy can be an admissible window for short time Fourier transform, but of course not all of them have some sense. We are going to choose such G's with some good properties, not only in time domain, but also in the frequency domain. Okay, our next question is how to calculate. So the question is how to calculate it. I mean, I have shown some of the results in 3D, in contour plot or like an image, but the question is how I calculated the short time Fourier transform. We have to recall that it has three terms, and let's say the simplest way how to calculate the STFT is if we group the first two terms together. If you are confused with this asterisk, it is only for, I mean, our g's in all of my examples were real functions. If they were complex functions, in that case, we must use the conjugate operator in the time domain, and of course, and then not in the frequency domain. But forget it for the moment, it's not so important. If all of our examples will be real, the conjugate does not mean a thing. Okay, so one way is to group x of t and to multiply it by some sliding window. How does it look like? For example, x of t of my voice could look like this. Okay, time is going on. What I do, I multiply by the window. In my example, the window will be rectangular. So my rectangular window cuts only this part, and I calculate the result. Then I move it to the right. Again, I move it to the right, I move it to the right, and so on, to the left and to the right. And when I go through all of these positions, I multiply the blue one and the red one and calculate the Fourier transform of the product. Of course, in practice, I cannot do that for an infinite number of that shifts where actually, so this is also t, but let's say the position of my windows was top. Actually, I can use some toe 1, toe 2, toe 3, and so on. If this set is definitely discrete, it is not continuous as it is in the equation. But of course, if it is dense enough, we can get nice pictures like I did in our previous slides. So of course, the time axis was not infinitely dense, but it was dense enough so to get the reasonably good result. What I did, it was actually discretization of the time axis, and we will discuss it a little bit later. But there's also an alternative way how to calculate. I mean, it's all good with this approach, but the other one will bring us to the filter banks. And filter banks will be the way how to realize not only short time Fourier transform, but also wavelet transform and all other stuff that we need as a bank of filters. So how to do that? So we still have three terms. Let us group it a little bit different. So instead of, I just changed the place of the two terms, and I grouped x, my voice, with cosine and sine, exponential term, okay? And separately, I have that g. Multiplication of my voice, multiplication of the signal x with cosine and sine results in some new signal. So you have some new signal, which is here in square brackets. And what do we have? Actually, we have a convolution of two functions. maybe it's easier to see that if we choose that omega equals 0. In that case, exponential part becomes invisible, it is 1. So it disappears. And now, since let's say the sign is incorrect, so I will use one extra minus to put it in order. So actually, this is convolution of my voice with mirrored time window. And conjugated, but forget it if the window was real. So what we do, we actually I calculate the convolution of x and time reversed localization window. Convolution actually corresponds to the response of linear systems. Maybe I would have to ask you, are you familiar with that fact that the operator of convolution is actually, if you want to calculate the response of a linear systems, you have to do the convolution of the input signal with the impulse response of such a system. Have you ever heard of it in some course that you have already attended? I suppose you were, but you don't look like. Tom is smiling. The rest
Yeah, I definitely heard of it, but maybe forget the specifics, you know.
Okay, I'll just try to make a sketch. Let's say this is a linear system. And if you apply delta to its input, and the linear system is empty, let's say the initial conditions are all 0, you got some response. The response is called impulse response, of course, because the impulse was applied to its input and the result was impulse response. Okay, now you have some general input applied to your system. How to calculate the result? Yeah, the result is actually some y, which is h convolution delta, or sorry, x. Okay, I'm going to use tau inside. So you have to calculate it over tau. Tau disappears from the result, and your result will be a function of t. So once you know the impulse response of a linear time invariant system, okay, I will just put it here, linear time invariant system. Once you have the impulse response, you can calculate the response to any input only by the convolution. Convolution is such an integral form where you have the first function here and the second function here. It is commutative, so don't care about which one is first, which one is second. This is the symbol of the convolution, the asterisk. And the actual realization is such an integral form where you have a first function and the second function, which is actually time reversed and shifted to the left and to the right to get the result. So this is something that is usually taught in courses like signals and systems usually on bachelor level, but also on some digital signal processing and so on. I mean, my example right here is about continuous systems and signals, but it stands for any linear system, including discrete systems and so on. So convolution is application of a filter. Filter is actually characterized by its impulse response, and in frequency domain, so it's called frequency response, H. Is it more familiar now? Can you recall it from some deep?
Yes, for sure.
Okay, then. So let's go back with our presentation. So if we just group it differently, in that case, so we have that convolution. Convolution is nothing else but the response of a linear system. So in our case, it looks like this. I won't be lazy, so I will draw it again. So I applied X to a filter, actually a linear system, and I got the result, only the result, I mean, with omega equals 0, of course. So X of 2 and omega was 0. Here I had minus. Reverse in time corresponds to conjugate in the frequency domain. Conjugate in time domain corresponds to minus to reverse in frequency domain. Okay, so we can calculate a part of the result by linear filtering. Oh. So let's imagine that this is the spectrum of my voice. I'm not sure that I can sing to produce such a spectrum, but let's imagine that it is the spectrum of my voice. Okay, now I apply the filter. The filter can look like this to my voice. Let's say this is G. I mean, my drawings are modulus of the spectrum. Maybe it's better to put it this way. If this is the spectrum of my voice, I apply such a filter to my voice. Convolution in the time domain is multiplication in the frequency domain. Actually, my filter takes out only a small part of the spectrum of my voice and proceeded to its output. So that's on the slide. This is the result. Okay, what happens if I multiply my voice with such an exponential? What happens here? If I multiply it, it corresponds to the shift in frequency. So the blue one will be moved. Okay, I will move it a little bit. So okay, I move it down. The red one remains where it is, and I move the blue spectrum up and down. And the red one takes out the different parts of the spectrum of my voice and put it on its output. So this is the other way how to calculate the result. On the next slide, we will see that, of course, we are going to choose only a few such frequencies, not all of them. If the first approach was slicing our time frequency plane vertically, now we are slicing our time frequency plane horizontally. Slicing, we are actually on the left-hand side, you can see a bank of filters. They are all the same, like this. And actually, we are moving the spectrum of my voice up and down. We are shifting it by omega 1, omega 2, and of course, we can do, in theory, we can do it for every omega. In practice, we are choosing only a discrete set of omegas and getting the results of filtering. But alternative is that I just put it where it is and I move the filters. Instead of having only one filter, I can have different filters that works. I mean, they have the same shape, but they work for different frequencies. The result will be the same. I mean, I can move the blue one, or I can move the red one. On the right-hand side on the slide, you can see the alternative way. So instead of having the same filter like on the left-hand side, right here we have filters that have shifted frequency responses by omega 1, by omega 2. So I'm moving the right-hand side. Okay, but the result will be on the wrong place, so the result must be shifted back. So that's why we need multiplication by the exponential part at the output of the filters. In both cases, we have a uniform bank of filters. On the left-hand side, you have the same filter repeated, and we are moving the spectrum of the original signal. On the right-hand side, we have a real uniform bank of filters. They're all the same, but their frequency responses are one near the other. So maybe I can just make a sketch of such a thing. So we have a sketch of filters that have frequency responses, and every one of them is responsible for a part of the spectrum. And here is the spectrum of my voice, and the result of multiplication is, of course, cut out the components of my spectrum. Some of the first speech analysis, even before the Second World War, were made actually by filters that were mechanical, electromechanical filters. So we had a microphone, some kind of amplifier, then the coil and the magnet. And the magnet was moving some metal plate with different, I don't know how to say that, needles, or I don't know what rods. They were resonating on different frequencies. So they were actually acting as a bank of filters. And here there was a human speaker. The filters were resonating on different frequencies, and some kind of ink was attached to the end. So there was a piece of paper to get the time axis. So the paper was running as the time was going on. And let's say the ink was projected on the paper, so it was the first possible analysis of the spectral content in time of human speech. Of course, we do not need to have such a system. It is much easier to us. We can do it, everything we can do it on digital computer. I mean, on this slide, the filters are still continuous. They still live only on slides, but very soon we are going to convert it to discrete way. Even here, we have chosen a discrete set of frequencies, discrete set of shifts. So we just arrived to discrete short-time Fourier transform. It is since we have a resolution that is linear, linearly dependent on time shift tau and linearly dependent on omega, it is obviously we need to do some uniform quantization. We actually choose some quantum of frequency, some quantum of time, and instead of calculating all the shifts, all possible shifts, we calculate only a discrete set of shifts and discrete set of frequencies altogether. So it is some kind of, it is, since the resolution is like it is obviously okay to do the uniform quantization of the time frequency plane. Right now, the result will be actually discrete. So the spectrum is on some points, like on nodes of this grid, this rating. Now the question is, can I restore X from only a discrete set of the points? The problem is now not so trivial as it was for continuous in continuous case. Decomposition into such a discrete set is called Gabor expansion of the signal. It is actually discretized short-time Fourier transform. And right now, it is not enough to have a finite energy G. There are several more conditions. It leads to something that is called frame theory. It is beyond the scope of our presentation, but I can only say that the quanta must be small enough, so the grating must be dense enough to provide that such a reconstruction is possible, that the inverse equation is possible. Instead of going into the difficult mathematical theory, we will learn how to design filter banks that already have that already satisfy the conditions for the perfect reconstruction. So much for the first lecture.